Hi, this is Ms. Dahlberg. Welcome to AP Chemistry, and we are talking about kinetics today. So we're going to talk about reaction rates, orders of reaction, and rate laws. So let's get started. So when we talk about kinetics, we're talking about the rate of reaction, or how fast a reaction happens. And we can talk about it in several different ways. We can talk about how fast a reactant disappears, how quickly a product appears, or the rate at which the overall reaction proceeds. Now, in order to do this, we are going to look at the change in concentration over a period of time. And so the unit for the rate will be molarity over some unit of time. Now, this unit of time might be in seconds, it might be minutes, it might be hours, it might be years. It might take years for some things to react. So, but we're going to look at change in concentration over change in time. Okay, so when I told you we're going to talk about 3 different ways. So if we talk about the rate of disappearance of a single reactant, in this reaction, A is one of our reactants. And so if we look at rate of A, it equals the change in the concentration of A divided by the change in time. Now, if you're talking about a reactant, there's a negative sign here, and that is just to fix the convention that rates, when we talk about it for kinetics, are always going to be positive. So if you come out with a positive rate, add in a negative sign, change it to a positive, it's not a big deal. When we talk about products, if you look over here, D is a product. So if we talk about the rate of D, we're talking about the rate at which it appears. And we're going to talk about the change in concentration of D over the change in time. So if we talk about the rate at which one species appears, we can find rates at which all the other species either appear or disappears. So if we know the rate of one thing in a reaction, we can figure out the rate of everything else. How can we do this? Because we know stoichiometry. And we know, like, for example, for every 2 of these that break down, we'll produce 1 oxygen and 2 of these. So, and in order to express that, the rate of reaction equals 1/2 times the change in concentration of T. You notice this little number right here is the coefficient, equals the change in concentration of oxygen divided by T. You do have a coefficient here. It's an understood 1. But we don't need to write that because it's 1. And then for the last one, looking at the rate of appearance of nitrogen monoxide over time, if you notice, it has a coefficient of 2, so there's a 2 down there. And so you can also kind of treat that as a mini stoichiometry problem as well if you're looking at finding the rates of reactions, and we'll talk about that later. And so we come to this graph. Now, you have seen a graph like this, and we talked about equilibrium before. You have concentration over time, and if you notice, this graph kind of curves, and then it starts to flatten out. Hopefully, you remember what's going on over here when it starts to flatten out, that you are reaching equilibrium over there. But this part, it says that the instantaneous rate equals the slope of the tangent line. And so why would that be? And so if we look at rate, we already said, is the change in concentration, change in molarity, I'm just going to put molarity in the bracket, over the change in time, right? Well, if we look at the change in molarity, this is the rise. And if we look at the change in time, that is the run for this graph. And so then we get what you know to be the slope. The rise over the run is the slope. And so that is why the rate of that reaction equals the slope at any point in time. Now, something to note, the rate at the beginning is much, much higher than it is at the end. And a couple ways we can tell that. If you look at this, the slope right here, if we draw a tangent line right here, the slope of that's really, really high. That's a steep slope, which gives us a really big number. So that has the highest rate of reaction. It's the beginning of the reaction. Things are happening quickly. As the reaction goes on, the slope changes. It's less and less steep, which means the rate is going down until we reach some point over here, which hopefully you remember is equilibrium. And at equilibrium, the rate is 0. Why? Reaction's still going on, but the change in concentration for the products and reactants, it's not changing anymore. It's staying the same. So time keeps getting bigger, but this becomes 0. So if we look at this reaction, and this is similar to something you've seen in the past, if you look, we start out with all nitrogen dioxide, and so it starts out really high. The other two start out at 0. We have none of those yet. And this reaction kind of decreases, or the concentration kind of decreases until at some point where it looks like it's reaching equilibrium down here. Now this has a negative slope the whole time because it's disappearing. These have a positive slope because they're appearing. And so something to kind of take note of, if you look at these two, they have different coefficients. And so you have different amounts of nitrogen monoxide and oxygen being formed, which we indicate by different concentrations. If you look, they both start at 0, but this one ends up with a higher concentration. This graph right here kind of mirrors this graph right here. Why? They have the same coefficient. This one, a little bit less. So, but could you identify, if you were told that you started with only one of these, could you identify if these little labels were gone, which is which in this one? Could you find the rate at any point in this reaction? How would you do that? You would, of course, you'd have to have numbers on the side, but you just draw a tangent line and find the slope of that line. Okay, so let's take a look here. We have AB, and if we look at this box right here, all of these are AB. They're all reactants. We have no products in here. When you move to the after, which looking at the time is 1 minute later, 60 seconds later, after we have only 1, 2, 3, 4, 5. 5 of those left. And if we count all these before, we have 15, which represents our molarity. After, we have 5 left. And so that tells us about 2/3 of that reacted and formed products. Okay, so how would we calculate the rate of that reaction for the first, I guess, minute of time? So let's look at that. So if we look at the rate of disappearance of AB, there's a few ways we can do this. We can look at the change in concentration of AB. If we start with 15 and we end up with 5, now this is always the final minus the initial concentration. Anytime, oops, my pen went out on me. Anytime you have this little delta, it always means final minus initial. And so our final concentration is 5 molar. Our initial concentration is 15 molar. Our change in time is 60 seconds. And so when you subtract that, you get 10 over 60. And when you do the math, you get 0.1667. Now, if you didn't remember that it's disappearing, you would come up with a negative answer, change it to a positive, and you're good to go. The units are important. The units are molarity per second, or molarity for whatever unit of time they give you in the problem. But the units are important on these. Now, you didn't have to do this problem using AB. You could have started with a rate of appearance of A, or A2. Now, if we did that one, if we look at A, the rate of A is the change of A over the change in time. And if we did the final minus the initial, then we have an initial concentration of 0. We had none of that product. Our final concentration, we formed 5 molar, and that was given to us in the problem. So if you look at that 5 molar divided by 60 seconds gives us 0.0833. You could have also said, hey, I have the rate of one of these. I can use stoichiometry and get the rate of the other. And so instead of doing this part for A, you could have gone back to this answer right here and said, okay, I know the rate of AB. If I want the rate of this one, well, I know it's going to appear at half the rate. So if you just divide the rate of this one by half, because if this is in a ratio of 2 to 1, this is going to disappear twice as fast as this appears. So we have half of that, not half of that previous answer. So one of these you had to do this way. The other, you had your choice. You could either do it this way or this way. Okay, now we're going to talk about the third one. We're going to talk about the rate of the overall reaction, which brings us to writing a rate law. Now, if you have a reaction, I told you that the rate equals the change in molarity, change in concentration, over the change in time. This is the rate for the overall reaction. That accounts for the change in concentration of all of the things that affect the rate. And so if we look at that, the rate of the reaction for the overall reaction equals K. Now this is a lowercase k, not the same as the one from the equilibrium, which is known as the rate constant. Similar to the other K, it is specific to temperature. So it is at a certain temperature that you would get that rate constant. You change the temperature, you change your rate constant. But if we look at our two reactants, we have K times the concentration of A raised to some power, and times B raised to the concentration of B raised to some power. Now, unlike, and this is big, this is one of those things that students tend to get wrong. Unlike equilibrium, M and N are not coefficients. Those are not coefficients. Those are, in terms of the reaction, you have to determine the reaction order, and it has to be determined from experimental data. You cannot just look at the coefficients. So let's talk about that a little bit. So like I said, you cannot predict it from the balanced equation. Cannot be predicted. You have to find it through an experiment. Now, one of the things that kind of easy about this one is that your reaction might be zero order, it might be first order, or it might be second order, meaning that those little exponents, M and N, could be 0, 1, or 2. So if you had the rate equals K, the rate constant, times the concentration of, let's just say you had one reactant. And let's say this little coefficient is 0. What does that mean? That means the rate is only affected by the rate constant. This is 0 order. The concentration of A does not matter at all because A to the 0 power is 1. So we don't have to worry about that. Okay. So looking at this, what if this is to the first power, which is the same as saying the rate is K times A. That would be first order. This little exponent is 1, so it's first order reaction. If it were 2, it would be a second order reaction. So that part's easy enough. Now I will say that these are the ones that you're going to have to worry about for reactants. They can actually be fractions. We don't have to do that, but just so you can know, they could be third order. We are not going to do that for individual reactants, although it might be third order overall. We might do a third order overall reaction. So if you have two reactants, for example, let's say you have A and B is raised to the first power. It is first order in A. So let me kind of write that here. First order in A. Second order, it's not, sorry, I'm looking at B, thinking it's A. So it's first order in B, second order in reactant A, and overall, add up all the exponents, it's third order. Okay, now what does all that mean? So if something is 0 order, if you double the concentration of that species, it doesn't affect the reaction rate. So if I give you 1 molar or 20 molar, doesn't matter. It's going to happen at the same rate, and the concentration doesn't matter. If you double the concentration, it still happens at the same rate, whatever K is. So K, the units for K for this would just be, since rate has to be molarity per unit of time, like seconds, the units for K would be molarity per second because these two are equal. So they have to equal each other. Okay, and so what would happen is you'd see a graph that looks something like this. You would have a graph of molarity on this axis, time on this axis, and you would see a straight line. It keeps going in a straight line. Nothing really affects it. The change in concentration doesn't change the rate. It has the same slope. And remember, we said the slope is the rate. The same slope, the same rate the whole time. So the slope of that line is K for a 0 order. Okay, now if we get to first order reactions, if you look at this, this is the rate law expression for a first order reaction. You have K times the concentration of A, and it's raised to the first power, which means that you have K times the concentration of A. That's it. If you double this, you double the rate. If you triple A, you triple the rate. Okay, so if you look at this, this just goes through what we already talked about. If you have an overall reaction, for example, you have some reaction of A plus B forming some product, and we'll call it AB. If It is, I think we said earlier, second order for reactant A, first order for reactant B. We'll just say M and N are first and second order. Then the overall reaction order would be M plus N, or 2 plus 1, and it would be third order. Okay, now here's the kicker. For the big K, for equilibrium, we didn't have to worry about units. Little k, not quite the same. So rate constant, if you're ever asked to find the rate constant or give the rate constant, I guarantee you I am going to ask you for the units. Now here's a list of these. You can write this down and you can memorize it. I'm not a big fan of memorizing because as soon as I memorize it, I walk away 2 seconds later, I forget it. Easier to understand where this comes from. So if you have a zero order reaction, your rate equals K. For all of these, the rate equals something. The unit of the rate is always molarity per some unit of time, and we're going to go with seconds. If this side has to equal molarity per second, this side has to equal molarity per second. Since there's only one thing on this side, its units have to be molarity per second, which is written m s to the minus 1. Why? This is harder to write in a typewriter or computer program than this. This is easier to type out. So over here, first order reaction. Your rate law for that would be rate equals K times only one thing. This raised to the first power. So on this side, if this rate equals molarity per second, on this side, it has to also equal molarity per second. Since this gives you the molarity, K has to just be 1 over seconds. And if we go back and look at that, if this is molarity, the unit of that is molarity, this has to be 1 over seconds, and you multiply those two guys, and you get molarity over seconds when you multiply those two. So K has to be 1 over seconds, or seconds to the minus 1. For second order, same thing again. We have molarities per second for rate. Over here, you have K. Don't know what K is, but I know I have molarity squared. So if I need this to equal molarity per second, and I know A is going to give me units of molarity squared, K is going to have to be, let me write that right here. If this is molarity squared for A, I'm going to write K right here. What do I have to write right here? So when I multiply this times molarity squared, I get molarity over second. So what do I need to do to get that? Well, first thing I need to do is I need to put in seconds. So I'm going to have seconds in the denominator because I need to get seconds. But I also have molarity squared, and I only want molarity once. So I need, instead of having molarity up here, like I did up here on zero order, I'm going to have molarity times seconds in the denominator. So let me write that a little bit bigger. So I have molarity times seconds. And when I do that, this molarity will cancel out one of those, and I'll have molarity over seconds. So the unit of K, so this is K right here, is 1 over molarity times seconds. Another way to write that is molarity to the minus 1, seconds to the minus 1. Same thing goes for this one. If you have A to the third order, now you're going to have to equal molarity per second on this side. You're going to have molarity cubed from this term. So K has to be 1 over molarity squared times seconds. And that way, these two this molarity squared cancels out two of those, leaving me only one molarity in the numerator, seconds in the denominator to give me meters per second. So this term right here, 1 over molarity squared over seconds. So I have molarity to the minus 2, seconds to the minus 1. Okay. So I said that you had to figure out the order of a reaction based on experimental data. And so let's look at, this is the kind of information you'll be given. And you have 3 experiments, experiment 1, 2, and 3. If you notice in the first one, we have 2 reactants. We're given a higher concentration in the first experiment, a lower but the same in the next 2. For the hydrogen, we have the same for the first 2 and a lower one for the last one, which is kind of an important way to set it up. Okay, so our job is to figure out what's the rate law, what's the rate constant, and what's the order for the overall reaction. And so you're given this data, and that's what you have to look at to figure out where you're going from there. So if we look at that, we have the rate for the 3 different reactions. If you notice for the first one, it's higher, and it goes down as you go through the different ones. So let's find the rate law. So to set it up, we would write the rate from experiment 1 over the rate from experiment 2 equals K times NO to the N times H2 to the M. Let me go back and let's look at that. Let's go back to the page with the reaction written. So what are we doing? We're saying experiment 1 has a certain rate. We even know the number. Look at that. But if we write the rate law will be written rate equals, and this is the rate law for the reaction, equals K, some constant, times the concentration of my first reactant, NO, raised to some coefficient. We'll do M. The second reactant raised to some coefficient, and we'll do N. You may be tempted to put 2 and 2, but you will get that wrong every time. They will never do it where it accidentally works out to be the coefficient. Why? Because that's a misconception most people have. So they will never, ever give you one where it's actually the same as the coefficients. I might accidentally give you one in a practice problem, but they never will. So this is the rate of the reaction. So if we want to customize it for each experiment, what we're going to do is we're going to set it up and look for the first experiment. This is the rate law for that first experiment where you have the rate equals K times the first reactant to the N, the second reactant to the M. Then you have the rate of the second reaction. That equals K times that first reactant to the N power. This little 1 and 2 is just to like help you remember which reaction you're doing. I typically don't write those. I label this side and hope you know where we're getting the numbers from. Okay, because I find this a little bit more confusing. It looks like a subscript or something. But what you do is you go back to that table and you take the rate from the first reaction. Now the rate, reaction 1 and reaction 2 should be pretty much, you know, they have the same K. The rates are a little different. Why? Because the concentrations are different. So if you plug in the rates, here's the rate of the first reaction straight from the data table. That equals K. We don't know K. times the concentration from the first reactant, right? We don't know what this order is. We don't know, so we just put N. For this one, this is a concentration from that first experiment. We put M. We don't know what that is yet. That's what we're looking for, these two guys. So then we jump down to rate 2. We're going to look at that. If you look at this one, whoa, too far. If we look at this one, we had a rate of 0.0225, and here are our concentrations for our two reactants. So those are what we have right here. Here's the rate, and here are our two concentrations. Again, we don't know these two numbers. Now, if you look at this, we can start doing some math. I have a calculator, and I can tell you that 0.9 divided by this number, 0.09 divided by 0.0225 gives me 4. If I come over to this side, I don't know what K is, but it doesn't matter because it's the same between the first reaction and the second reaction, so it cancels. Now here's something even cooler. I don't know what M is, but I know 0.3 to the M divided by 0.3 to the same M cancels. So now I can just look at one of my reactants. So I'm only looking at the nitrogen monoxide here. Here's the concentration of the first reaction. Here's the concentration of the second reaction. If I have it to the N power, I don't know what N is, but it's the same for both. If I divide these two, I get 4 equals 2N. 2. Okay, let's see. My pen must have turned off. Okay, so this has to be N. Now, 2 to the what power gives me 4? 2 to the second power gives me 4. So I know that N is 2. So this is what I call the algebra method. This is the algebra method. We'll also look at table logic and look at it from a table standpoint. And I'll probably do that in class. Now, to do that, to do the next one, you look at experiment number 2 and number 3. So what we did in this first one, comparing experiment 1 and 2, we had one reaction where the concentration changed. And the other reactant stayed the same. Now we need to do that again, but we need to figure out what is the little exponent right here. I don't know what this one is. So now to figure out this one, I need a reaction where the two experiments have a concentration of this one that changes. And for the other reactant, since I'm not interested in that, I already know that this is 2. I need these two guys to stay the same. So if we set that up just as we did before, if you do the rate of experiment 3 equals, and write the rate law for experiment 3, over the rate of experiment 2, and this is the rate law for experiment number 2. Now, if you did 2 over 3 instead, it's fine. In fact, it might be even easier than the way it's set up here. I probably would have flipped it. I kind of like the bigger number on top, but it doesn't matter. If you write in the rate for experiment number 3 and the concentrations for experiment 3, the rate for experiment 2, the concentrations from experiment number 2. If you divide these two, you get 0.67. We kept the reactant, the first reactant, the concentration the same, so that cancels. As well as K. K cancels. It's the same for both reactants. So now we really are only comparing our second reactant, the hydrogen. So I have 0.2 over 0.3, both of them raised to the m power. So I have 0.67 equals 0.67 raised to the m. Now, if this doesn't change, this exponent here must be 1. It must be raised to the first power. So in other words, that if the concentration of the hydrogen goes up by half when we keep the nitrogen the same, and the rate goes up by half, by the same factor, then it must be first order. So this must be first order. So if we write our overall rate law, we can go back and we can write rate equals K. For this one, we found out it was second order. For this one, we found out it's first order. And so this is our rate law. This talks about table logic. We're going to go over that in class. And this is known as the algebra method. Sometimes some people call it the ugly algebra method. I think this method is important. I think it's important to do both. For the most part, it's easier to use table logic. However, the algebra method works for harder ones, so sometimes some numbers are a little bit tougher to figure out. Now, to find the rate constant, you would take your rate law that you just uncovered. Rate equals K times NO squared times the H2 to the first power. And you pick an experiment. You pick any experiment in there. It doesn't matter which one, and you solve for K. You plug in the rate, and this one is using the first experiment. You have 0.09 for the rate, divided by NO2, which is 0.2 in that experiment. The hydrogen is 0.3. So when you square this one, multiply it by that, and take that answer and divide it into this one, we get 7.5. Now, if you were careful with your units, if you notice, you have molarity on top, seconds in the denominator, molarity squared in the denominator, and another molarity in the denominator. So if you cancel, you get molarity, cancel molarity, and now I have seconds in the denominator and molarity squared in the denominator. And this is another way to write that. Again, units are important. I will always ask you to write the units for the rate constant. Okay. And we're going to stop here, and I will see you next time.